All right, today we're going to pull back the curtain on this really clever mathematical tool that engineers use. It's how they master all those invisible forces inside, pretty much every machine that moves. It's called co-energy. And honestly, it's a brilliant piece of thinking that basically makes our modern world possible.
So, how do you actually calculate the invisible forces that make a motor spin? I mean, at first glance, that seems pretty simple, right? But the answer? Well, it opens up this fantastic story of ingenuity. Because to really get a grip on the forces inside a motor, you need more than just the obvious approach. You need a shortcut, a really clever one.
And that leads us right to the core problem, the real challenge here. Calculating the precise force or torque in any of these electromechanical devices, it's just not straightforward. There's this fundamental mismatch between how we actually run the machines in the real world and how the math wants us to do it. Okay, so here's the disconnect. In the real world, right, when you run a motor, what do you control? You control the current you're feeding into it. That's the knob you can turn. But the standard energy formulas? They're way, way simpler if you could control something called magnetic flux. Just think of flux as the total magnetic field passing through a surface. The thing is, we can't easily control flux directly, so the math just gets messy. It's a real practical problem. And this is where our hero, co-energy, enters the story. I love this part. Faced with this mathematical headache, engineers didn't just throw up their hands. Nope. They invented a brand new tool, a concept designed for one reason and one reason only, to solve this exact problem. So what is this thing exactly? Well, co-energy is a mathematical concept. It's purpose-built to make calculating force simple and practical, especially for those real-world situations where, you guessed it, current is the thing you're actually controlling. Now, it's not a physical energy you can go out and measure with a meter, but think of it as a super powerful analytical shortcut. Okay, so how does this magic tool actually work? Well, the easiest way to wrap your head around co-energy is to think of it as the complementary twin to the magnetic energy we're all a bit more familiar with. They're like two sides of the same coin, and their relationship is, well, it's beautifully simple. Just take a look at their mathematical definitions. You've got magnetic energy, which is the integral of current with respect to flux linkage. And flux linkage is just the total flux linked by a coil of wire. Then you have co-energy. And what is it? It's the integral of flux linkage with respect to current. They are perfect mirror images of each other. They just swap the roles of current, I, and flux linkage, lambda. Pretty neat, right? And what's really cool is this simple, super elegant equation right here. It shows that when you add magnetic energy and co-energy together, what you get is the total potential energy in the system, represented by the product of flux linkage and current. They literally complete the whole picture together. Okay, I know that might feel a little abstract, so let's bring it back down to earth. What does this all look like in a simple, linear system? A system where everything is nice and predictable. So in this very common case, where the inductance, L, is constant, something kind of magical happens. The formula for magnetic energy becomes 1/2 Li squared. And the formula for co-energy? You guessed it, it's exactly the same, 1/2 Li squared. They are exactly equal. And this just brilliantly illustrates the core idea. For these simple linear systems, energy and co-energy are identical. They split the total energy of the system perfectly, right down the middle. Okay, so we've defined our tool, we understand its relationship to energy, now it's time for the payoff. How does this super elegant concept solve our original problem? The whole how do we calculate the force thing. And this is the beautiful part. That whole complex problem gets boiled down to 3 super straightforward steps. Step 1, you define the co-energy for your system. Step 2, you differentiate that co-energy with respect to position. And step 3, the result is the force. It's that clean, it's that simple. And here is the crucial formula that makes it all work. The force, F, is simply the partial derivative of the co-energy with respect to position x. And this is key, you do it while holding the current, I, constant. This perfectly matches the exact conditions of the real world, and that, right there, is why this tool is so incredibly powerful. And of course, it's not just for things moving in a straight line. The exact same logic applies to things that spin. For a rotating machine, the torque, T, is just the partial derivative of co-energy with respect to the angle of rotation, theta. And again, you're holding that current constant. It's this same beautiful principle. So, okay, we've got these really neat formulas, but let's connect this back to the real world. Why does this elegant shortcut actually matter? What's the impact on the technology that's all around us every day? Well, it really boils down to a few huge advantages. First, it makes the math way, way simpler. Second, it's basically tailor-made for the practical situations where we're controlling the current. And maybe most important of all, this method works flawlessly for both simple linear systems and those much more complex nonlinear systems you find in really high-performance machines. And get this, there's a really fascinating physical insight that comes out of all this math. It gives us a new rule of thumb. Force or torque will always act in the direction that increases the co-energy. It's this incredibly intuitive way to predict which way something is going to move. It's almost like the system is trying to find its most comfortable state. And I want to be really clear. The principles we've been talking about, they're not just some abstract academic idea. No way. They are fundamental to how we design and analyze the electric motors in your car, in your blender, the little relays and solenoids that act like electric switches, all those countless actuators and rotating machines that literally power our world. So in the end, co-energy isn't just another formula in a textbook. It's really a testament to engineering creativity. It's a purpose-built tool designed to take a really hard problem and make it simple, which kind of leaves us with one final thought, doesn't it? What other elegant shortcuts, what other clever tricks are hidden just beneath the surface of the technology we use and rely on every single day?